Hello everyone. Welcome to lecture 1 of CS 531 Memory Systems and Architecture. So in this lecture we will discuss about the basic introduction about computer and memory systems. But before starting today's lecture, let me remind you about the weekend tutorial of Gem Sim Simulator. So this simulator is very helpful and it will uh, help you to do your term paper efficiently. So if you want to save your time and if you want to do a good term paper, I'm strongly advising you to attend this tutorial as well as the tutorial of the next weekend, and the details of the tutorial will be shared very soon, and I'll also share a link and through this link you have to confirm that you are attending this tutorial. I'm not forcing you, but if you are not attending, then it is your responsibility to understand this simulator and then continue your term paper. Okay, so this lecture I will start from the very basic of computer. So but I'll cover all the basic very quickly, and I'm trying to cover all the basics by this week so that we can start our actual content of this course by next week. So the basic of chip designing start with this component. This is called transistor. But as a computer science student, we see that the starting of a circuit from this, like we know it from digital circuit. So we know it from this level. But actually, these gates are actually designed with transistors. So the main component, basic component, is transistor. And we know the Moore's law. And what is Moore's law? According to Moore's law, the number of transistor in an integrated circuit is increasing or doubles approximately in every 2 years. So this is Moore's law and this is still valid. Okay, then now I'm quickly moving to computer. So if I'm not showing you the complete low level details of computer because it's an advanced course, and I hope you already know a computer, and I am also hoping that if you already know the internal component of a computer, at least you have opened a desktop computer in your life. So these are some common components of a computer. This is the CPU, memory, input output, and interconnects. And inside the CPU, you'll find register, arithmetic logic unit, control unit, and internal CPU interconnect. These all are the part of a CPU. And if we go for different memory components, then these are the memory components of a computer: cache memory, main memory, and secondary memory. So secondary memory means the hard disk, main memory means the RAM, and cache memory, and in detail we'll explain what is called cache memory here. But uh, actually, these cache memory is part of a CPU, and that's why this cache memory is called a on-chip memory. So if I explain it in more detail, then if we go to a market and if we purchase a processor, for example, if we go to market and purchase a Intel i7 processor, then inside that processor, the cache memory will be inside that processor. But if you know where the main memory, that is RAM, where we place in main memory, if you see a motherboard or if you open a desktop, main memory or RAM is placed outside that chip, right? Outside the processor. It is installed in the motherboard, not inside in the CPU. That's why cache memory is called a on-chip memory, and main memory is called off-chip memory. And the secondary memory is you can consider as a hard disk or SSD. These are the very common point regarding computer, and you already know all these things, so just let me just read all these points. I hope you will agree with this. Every computer must able to perform some arithmetic operation. Computer only understand machine language. Compiler converts a high level code into assembly language code. An assembler convert the assembly language code into machine language code. So each assembly language has a set of instruction called instruction set architecture. So the meaning of the entire content of this slide is, if we write a C program that is a high level language and we compile it, then compiler will first convert it to a assembly language code, and then there will be assembler which will convert this assembly language code into machine language code. What are the assembly language code? Assembly language code has some instructions, and these instructions are called ISA, instruction set architecture. So I think most of you here know at least one ISA. And if I see the list of the students, and most of you have either from 2017 BTech or the MTech students. So both of you, I think, know the risk instruction set architecture, which Dr. Kalyan had already taught you, right? So if you want know at least one ISA, that is enough. So here I have shown some example of some ISA like MIPS, x86, ARMS, all these things I have explained here. So this is an example of instruction. And uh, this is a assignment, actually ungraded assignment. Then if this is the expression, and if you want to write a corresponding assembly language code for this, then how to write, then you can try it by yourself. And there is no restriction, either you can go for MIPS or any other assembly language code, it is up to you. Then memory operations. So if this is a CPU, I'm assuming this is a central processing unit. So what are the component inside the central processing unit? In central processing unit, normally the most important component is arithmetic logic unit, right? And there will be some registers. So if you want to perform any operation with arithmetic logic unit, then the value must be stored in register pass. For example, suppose there is a register here and there is a register here. So if you want to perform addition of two values, then one value must be available in this register and another value must be available in this register, and then only the arithmetic logic unit will perform the addition, and result will be again stored back to some another register. Okay, so for example, suppose this is memory and this is the CPU. Memory means, assume that this is RAM, this is memory, and this is the processor. So I'm quickly need to explain here about what is called von Neumann architecture, because all the computer, even laptop, mobile phone nowadays are still following von Neumann architecture. So according to von Neumann architecture, all the data are initially in the memory, and if any processor need to do any kind of operation, then it has to fetch the data from the memory to the processor first, and then it will perform the operation, and after the operation the result may be again returned back to the memory. So this is how a computer works according to von Neumann architecture. Initially everything is in memory, and one by one you have to fetch the required content to the CPU, and you have performed the operation in CPU, and after the operation you have to write the data back to the memory. Okay, so now let us consider this is the base address of memory. This is the base address, and this is base address plus 1, plus 2, plus 3, like this. And let me assume that I have to perform this operation, r equal to a plus b plus c. So what is a here? Assume that a is this memory location is a, this memory location is b, and this memory location is c. So what I need to do is I need to add the content of this memory location plus this memory location plus this memory location, and final result I need to store in this memory location. So how to do it? For doing this we need a program, right? Because this is a high level thing, so when you will convert it, it will convert to this type of assembly language code. So this is the corresponding assembly language code, and assuming that this assembly language code will be executed in CPU one by one. So the first code is saying load from this address 0 plus register 1. So assume that register 1 stored this address, base address. So base address plus 0. So first of all, it is saying that load from this memory location and store it in a register. So it will load 141. And then the second instruction is said load and store load from base plus 4. Base plus 4 is this address. So load from this memory location and store it in register 2. So 170 will be stored here. And then third instruction is saying add instruction. So it will add this two. So here arithmetic logic unit will perform a operation. It will add these two and store the result back to register 2. Okay, and then there will be another load instruction which will load the content of C here 523, and then there will be again another add instruction here which will add here the final result is 734, and the after this final result is here, so the last store instruction will store the content of this register back to this memory. So this is how a computer works basically. Initially everything in memory. So only one thing concept that I have not explained here is that this program is also initially stored in memory. So first of all, this program will load one by one, instruction by instruction from memory to computer, and then this instruction will execute here, and based on this requirement of this instruction, this data will be fetched here. So you always have to remember there are three kind of interaction with the memory. First interaction is fetch instruction, and then based on this instruction, if there is a load instruction, then it will load a data from here to here, and if it is store instruction, then it will write a data from CPU back to memory. So fetch, instruction fetch is one type of communication between CPU and memory, and other two type of communication are load and store. Okay. So these are some example of syntax of MIPS instructions ISA. But if you know any other ISA, that is fine, because in this particular course, knowing the syntax of ISA is not required. Just to understand the basic concept of computer, it is required. But specifically, I will not. I must inform you at the beginning that the detailed syntax of any ISA is not required for this course. So I'm not explaining all these things, but I'll share the slide with you. If you want to clear any doubts, you can go through these slides. These are actually explaining the syntax of MIPS instructions. This is the example of branch instruction. Okay, so this is a more detailed explanation about how computer works. See, in this figure, in memory, both the assembly language program and the data are all both are stored in memory. So first of all, if we know it from the your previous course, there is a register called program counter, right? So if the initial value of program counter, if initial value of program counter is 1000 here, then it means that next the data, the instruction stored in 1000 will be fetched here. So this means this instruction will be fetched from here to here, and after fetching the instruction will be stored here in instruction register. That is called fetch phase. This is called fetch. After fetching, the next part is to decode this instruction. So next call is decode. So during after decode, it will realize that okay, this is a load instruction. So if load instruction, it means that you have to go and load data from the memory. So from which memory address, that memory address will be calculated in execution stage here. And after this, in memory access, the instructional the computer will go and load the data from this particular memory address, and it will store in the register 1 here. So this is called memory access. And write back means if there is a data need to be write from here to memory, then it is performed in write back stage. So fetch, decode, execute, memory, and write back, all these stages are part of pipeline computer, right? And I hope you already know this from your previous course. So if it is not clear, please clear it from any basic computer organization book. So I'm not explaining it in detail. So now if we go and try to understand program counter in more detailed way, then suppose program counter means first of all it will fetch this instruction. After fetching this instruction, it program counter will increment by 4, and it will fetch this instruction, and again program counter will increment by 4, it will fetch this instruction, then this. It will go like this if the program is sequential. But in this particular case, this two, after this it will fetch this instruction, and after this instruction, this is a branch instruction. So after this program counter, there is a two possibility of program counter. Either it will go to this or this, right? If this branch is successful, then it will jump from here to here. If branch is not successful, then it will go here, and it will execute this instruction, and finally it will go here. Otherwise, from this else it will go to exit, like this. So I hope all this thing you know. And since and the overhead of branch decision taking, and how to remove the overhead of the time taken by a branch decision and all this thing we know, right? For example, if there is a loop here, and then this part will be executed multiple times, and in this case, if there is a predictor which will tell you that okay, this branch is every time it is taking or not taking, then it will save some time, right? And all these techniques are called branch prediction techniques. This is a very huge area of research, branch prediction. But since this course is based on memory systems, I will not go for any detail of branch prediction and all. This is not required, or just knowing the basics is enough. I'm not explaining this data path, but I am assuming that at least you should know a basic data path. So if you want to know more about this data path, you can follow this book, and at least you should know how a basic data path works for a computer. So this is program counter, this is the instruction memory, this is register. This basic data path should be clear to you. This is a more detailed data path. I'm not explaining it. I'm hoping you already know it. Again, I'm also reminding you that these concepts are not directly related to this course, but knowing it is better. Performance of a computer. Performance X means performance of computer X, and here in this term execution time X means execution time of a computer X. So now performance X means 1 by execution time. It means The more the execution time, the less of performance. For example, suppose here if the performance of computer X is more than performance of computer Y, it means that the execution time of X is less than execution time of Y. And also performance of and what is execution time here? Execution time means CPU time. So what is CPU time means, if you are suppose there are two computers, so two computers, so how you will say that this computer is performing better than this computer? So there are C1 C2, two computer, how can you say that C1 is performing better than C2? What the a possible ways, run a same program or same software or a same algorithm in both computers C1 and C2 and check which one is completing it faster, how much CPU time is taking to complete this algorithm. So that is called CPU time. So CPU time means CPU clock cycle required for a program, means if you are running algorithm, how much CPU cycle it is taking, and then clock cycle time means time required for each cycle. So that is called CPU time. So you can also calculate CPU time as CPU clock cycle required for a program divided by clock rate. That is very obvious. And what is called instruction count? Instruction count means the number of instruction executed in by a computer. For example, as I said, you run an algorithm or run a program on computer C1. So if when you run a program on computer C1, instruction count means by executing this program, how much instruction it has executed. And all these low level, it is like, if you write a program, first of all you'll compile it, so it will be converted to assembly language code, and then only when you'll run it, then how much instruction it is executed, that is called instruction count. Cycle per instruction, or also called CPI, means the average cycles required to execute a particular instruction, and the reverse of cycle per instruction is called instruction per cycle. So all these parameters are very very important for this course also. You should know all this parameter, what is called CPU time, what is called execution time, what is called instruction count, what is called CPI, IPC. All these parameters is required. Also means means which is better, means low CPI is better or high CPI is better, that also you need to understand. You can also this is also a formula to calculate CPI, CPU clock cycles for a program divided by instruction count. And then this is also a formula through which you can calculate CPU time. CPU time is instruction count plus cycle per instruction into clock cycle time. Instruction count means total instruction executed by this program, and cycle per instruction, so this is the cycle required for one instruction and it is the total instruction. So this is actually this CPU clock cycle for a program and then multiplied by clock cycle time. And this is another example, another way of calculating CPU time. All these formulas you have to understand. If anything is not clear, you can follow this book and clear all these basic concepts. And then I'm skipping this pipelining part. If you are interested, you can go through this slide. I'll share the slide with you also. But this is not directly related with this course. What I'm expecting from your side is that you should know the basic concept of pipelining. That's it. Nothing extra is required for this course. So I'm skipping all these slides related to the pipelining, what are the different types of hazard, how to calculate speed up, all these things I'm not calculating, not explaining. Okay, so this is the most important slide. From here, whatever I'll explain is very, very important for this course. So you may, as I have said, that whatever I explained before this slide, you may or may not know it properly, that is fine for this course. But if anything that all the basic concept that I'll explain from this slide, you have to understand it very properly, very very properly. And also point is, all the parameters that I have explained, for example CPU time, CPI, IPC, those are important for this course also. Except those parameters, other point that I said, instruction set, pipelining, all these things, it is important but not very very essential for this course. Okay, so from this slide we'll start with memory unit. So we'll start with memory unit. So as I've said, there are three types of memories. Basically, I'm ignoring the registers here. Registers are also kind of memory which plays inside the central processing unit, but I'm not considering it. After this memory register, there are three types of memory normally. What you first is called cache memory, and then the main memory and secondary memory. Also cache memory is divided into multiple layers, multiple levels: L1 instruction cache, L1 data cache, then L2 cache, and then last level cache. So the last level cache is no specific rules. Sometimes the L2 is also a last level cache, because if there are two levels of caches there in a processor, then L2 is your LLC. Okay, so remember this term LLC. LLC means last level cache. So many times in this course I'll use this term called LLC. So sometime if in a particular processor there is only two level of cache, then L2 is the LLC. If there are three level of cache possible there, then L3 is the LLC. In case of modern processor like i9 processor, there are four level of caches. So L4 is the LLC in that case. Main memory means the RAM of your computer. Secondary memory, as I said, is the hard disk of your computer. So in this course, basically what we will discuss, we'll discuss cache memory and main memory in detail. Also in terms of cache memory, basically we'll mainly cover most of the thing that we'll cover is part of last level cache. So you can say that the entire course is mainly based on last level cache and main memory. What how to improve the performance of these, how to reduce the energy consumption of these two memory layers levels. This is mainly we'll discuss. But before that, the principle of locality. Again, I think you know it, but why principle of locality? Because if I ask you a question that why cache memory and main memory are required, then the principle of locality is very important. Because as I have already explained, that according to von Neumann architecture, all the data is initially in the memory, and whenever processor want to do some computing, then the required data is fetched from the memory to central processing unit, right? So initially, suppose if this laptop is I switch off this laptop, then all the data will be in secondary memory, right, in hard disk. When so power on the laptop, again data slowly data will come, will fetch from the secondary memory, and it will be placed in main memory as well as in cache memory. So the question is, if initially all the data are present in secondary memory, and somehow we have to fetch all the data from secondary memory to perform some execution, then how this cache memory and main memory are giving benefits. Okay, one more important point here. I hope this is known to you. That's why I have not explained. But since it's a memory system course, so I think I should explain it, that cache memories are faster than main memories, right? And then main memory are faster than secondary memory. But cache memory is very expensive than the main memories, and then at last the secondary memory. So cost wise, cache memory is very expensive, and speed wise, cache memory is very fast. So cache memories are fast, then main memory, and then secondary memory in terms of speed. Okay, so now according to principle of locality, there are two types of principle of locality. One is called temporal locality, and another is called spatial locality. Temporal locality says if this processor is requesting for a particular data, then it is very likely that in near future it will request for the same data again. So if I repeat this line, then it's saying that if CPU is requesting for a data now, then it is very likely that in near future CPU will request for the same data again. So that is called temporal locality. And spatial locality means if the CPU is now requesting for a data, then it is very likely that in near future it will request the nearby data. So that this is called spatial locality. So to satisfy, since there is a cache memory here, so according to temporal locality, if CPU is requesting for a data, and then if I place this data in cache memory, then according to temporal locality, there is very high chance that CPU will again request for that data. And in that time, the data will be found in the cache memory. So it will save a lot of execution time, memory access time, because if we go for main memory, then access time will be very high, right? So that's why the advantage of temporal locality. The advantage of spatial locality is that if as it is said that if you request for a data now, means if CPU is requesting for a data now, then it is very highly likely that near future it will request for the nearby data. So to take the advantage of spatial locality, what we need to do is, when processor is requesting for a particular data, instead of just fetching that data, fetch a big chunk of data, right? Fetch a big chunk of data, that is called block. That is called block. Instead of requesting going to main memory and collect just one data, it will collect a block of data. Why a block of data? Because in according to spatial locality, in near future the CPU will request for the nearby data. So go to the memory and just collect all the nearby data also together. So that is called block. So if we go to this slide, so this is the basic definition of cache memory. Cache memory is an on chip fast memory placed very near to the core. I have already explained, right? It is a on chip memory, and it improves the performance of the computer. So design technology I'll explain more in more detail in next lecture, but here I'll just explain you that cache memories are designed with SRAM technology. Okay, so more detail will be cleared in next lecture, so I'm ignoring this point here. Next point is called block size. I think in previous slide I have already explained you the concept of block size. Block size means whenever core will request for a data, core will normally request for a particular word, but when it will go to cache, cache normally deals with a chunk of data that is called block. That is called block. So why this? Because according to get the benefit of spatial locality. So that is called block size. So normally block size are 64 bytes or 128 bytes, or sometimes it can be 32 bytes also. But the normal means standard size is 64 byte block size is very common. So every time when there is a miss in cache and cache need to go to main memory to collect fetch some data, it will go and collect 64 byte data at a time. 64 bytes of data at a time, because this is the block size. This is the you can also relate block size with the page concept of main memory. If you have studied operating system, then you know that if there is a miss in a main memory, it will go to hard disk and collect a page at a time. So the minimum data that need to be fetched from hard disk to main memory is called page, right? A page or frame. But here between cache to main memory, it is called block. And standard block size, as I have said, is 64 bytes. Some important terms related to cache, but before explaining all this thing, let me show you an animation here. So concentrate here. Suppose the core is requesting for a word called a. It is requesting for a data called a. So first of all, when core will request for this data, how it will request? As I have said, I'll ignore this low level details, but here in this slide I'll explain it with low level. But from next slide, from now onwards, I'll not explain. So here I said core is requesting for a data A, but how it will request? In reality, core is trying to execute a load instruction, right? If it is executing a load instruction, then after from this load instruction, it will request for a address like this. Read A, right? It is loading, it trying to load something. But in this course, I'll say core is requesting for a data. So core is requesting for a data A, or core is requesting for a word A. So first of all, the request will come here in cache, and it will search in cache that if the data A is here or not. Yes, it is here. The block is present. So it is called hit. So if it is hit, then data will be transferred from cache to core directly. It will save a huge time because no need to go to main memory. Now the next is core is requesting for a word called Y. So now when the request will come to cache, it will search in cache, and if you can see the y the block having y is not here, so it is a miss. So miss means the request will forward to main memory. So it will go to main memory, and where y is, this is the block containing y. So this block will be moved from here, it will be copied from main memory to, and it will store to cache first, and then the y will be transferred here. So this is not x, this is actually y. So because the core is requested for the data y, so now y will be transferred here. So this that was a miss, and after miss we have to go to main memory, fetch the data from main memory to cache, and then transfer this particular data to the core. So I hope you understand the concept of block here. So now if I go for some more requests, suppose next the core is requesting for this b, read b. So read b will be hit or miss. Read B will be a hit here because the block is here. So read B is hit. Read R will be a miss here, right? Read R will be miss here. So it will go here and it will fetch the entire block PQR, and it will store here. So read R is a miss. What about read P? Read P will be a hit because when there is a miss for R, then the entire block is now placed in cache. So read P will be a hit here, and read S is again a miss. So I hope you understand what is called cache miss, what is called cache hit, and there is another term is called miss penalty. Miss penalty means if there is a miss here, then what is the time required to fetch the data from main memory and store it here? That is called miss penalty of a cache memory. So all these basic terms, I hope you will understand. And again, it's not possible for me to explain all this term in more detail, so we have to You have to go to the you have to clear it by yourself. At least you should read once the basic concept from BTech level computer organization book. Okay. So now one more thing here. Here I said that core is requesting for a word like read A, read Y. So what are these A and Y? These are actually word address. So for example, if we know that memory, most of the memory are byte addressable memory. It means that every byte has a address, right? Every byte has a byte one, byte two, byte three, byte four, like this. Every byte has a address, and the most of the time the core request for a word. So what has a address? So suppose this is a word address. Normally the address are 32-bit address or 64-bit address, right? But here I'm assuming this is the address. Maybe it's 16-bit. I'm not sure. Yes, I think it is 16 bit. Assume that this is a 16-bit address. So if this is the address, word address, then core will request for this address. Core will request for this address. But if the block size is 64 byte here, that means uh, how many bits are required to represent 64 byte? 6 bit. So from here, the first 6 bit, these bits are actually block offset. We call them block offset because the block address will be this. When the word, suppose this particular word is requesting by a core here, but this word, it will belongs to this particular block. This particular block, this is the block address, because these 6 bit are actually offset. So when the block address will be this 000. Okay. So now I hope the word address and block address concept is clear to you. Now next is data management policy of a cache. Data management policy of a cache means there are three things. First, how to search a data in a cache, then how to place a data in a cache, and how to replace a data from a cache. This block placement is also called mapping policy. So based on these three things, three policy, searching, mapping, and replacement, there are different kind of cache memory possible. That is direct map cache, fully associative cache, and set associative cache. So one by one, I'll explain these three cache structure to you. But before this, let me explain you some parameters quickly. So these parameters were here. I'm assuming that there is only one layer of cache, that is only L1 cache memories is there. For example, here I assume that there is only one level of cache. There may be multiple level of cache also possible, like L1, L2, L3. But all these things I am not explaining now. From now, I'm only explaining that assume there is a core, there is a cache, there is L1 cache, and after L1 cache there is main memory or RAM. So in terms of this design, what is called CPU execution time now? CPU execution time will be CPU clock cycle plus memory stall cycle, because CPU clock cycle means number of cycles required to execute a program in CPU. But if there is a load and store, then it has to go to memory and then fetch the data if there is a miss in cache. So that is called memory stall cycle. What is memory stall cycle? Memory stall cycle means number of miss in the cache into miss penalty. Miss penalty means if there is a miss in cache, then the time required to fetch the data from main memory to cache, this is called miss penalty. So the number of miss into miss penalty is called memory stall cycle. And you can also represent this memory stall cycle as instruction count, and number of misses means instruction count, and then next will be here miss per instruction. Miss per instruction, this is the same thing. Also, if I want to represent it like this, number of instruction into memory access per instruction into, we can write miss rate here. So what is miss rate actually? You have to remember it. What is miss rate? Miss rate means memory miss per memory access. Then these are some other another formulas. This is also miss per instruction can be represented with these formulas. Try to relate these formulas. Maybe here I'll explain this formula. Miss per instruction, how means miss rate. So miss rate means memory access per miss per memory access. This is called miss rate. So miss per memory access into memory access, and then divided by instruction count. So this means miss per instruction. So try to relate all these formulas. Don't just memorize all these formulas. If you are just memorizing all these formulas, that will not help you. So try to understand all these formulas here the way I have explained. For example, number of misses means instruction count into miss per instruction. So miss in each instruction into total instruction, that is number of misses. So in this way you try to relate all these formulas, and all these formulas are written in this book. So if you, again I'm saying that if you want to understand them, try to read this book. And basically you need to read this appendix C from this book. And the last point is called average memory access time, or AMAT. It is very very important to compare the performance of two computer. So many time we will use arithmetic average memory access time to compare the performance of two cache memories. Okay, so this formula is hit time in plus miss rate into miss penalty. So you have to remember this thing, average memory access time. Okay, and so now I'll explain you the structure of direct map cache. The structure of direct map cache is like this. So assume that this is a cache where these rows are called sets, and this is called way. So there is only one way here. There is only one column. So the each row is called a set here. Okay, and now assume that there are addressing is 16-bit address. So this is the address. So basically when core is requesting for a block, or core is requesting for an address, then it will as I have explained previously, then when core is requesting for an address, then the request will first come to this cache memory, and we will search in cache memory. If there is a miss in cache memory, it will go to main memory and collect the data and store it in cache. Now the question is where to store it in cache, because there are many entries possible, there are many location possible in cache. So when there is a miss, and will go to main memory, fetch the data and store it in cache, where to store. So that is depend on the address. So assume that the address is of 16-bit here instead of 32-bit. Block size is 16-bit, 16 byte, and number of set is 8 as it is showing here. Number of set is 8. So how many bits are required to represent this 8? So there are three bits that are required. So index, this is set index bit. Set index bit will be 3, and offset bit will be 4. What is offset bit? Offset bit is the if the block size is 16, then 4 bits is required. So this is called offset. So now in this particular case, block offset of this from this address, block offset is 4 bits. Okay, set index will be 3 bit, and remaining is called tag address. So suppose this is a address of a word requested by a core. As in the previous slide, I said core is requesting for A. So here assume that this is the address of A. So basically core is requesting for this address. So if this is the address, and if I want to map this address here in this cache, then the first 4 bits are the offset bit. So they are not related for a block, right? So the block address will be all this. After this red ones, there will be 000. This is the block address. Okay, so first 4 are offset. After offset, the next 3 are called set index, right? These are called set index. So based on this set index, it will be decided, it will decide that where this address will map. This address will map to set number 7 because of this, right? This is called tag, and this is called set offset, and this is set index. Now this is a particular. So now in this case, if I try to explain this, then core is requesting for a particular word. This is a particular word. So here these 4 bits can change like this. This is another word of within residing within the same block. This is another word residing within the same block, and this is another word within the same block, and this is another word within the same block, and this is called the block address. Block address means this will be 000. You can change it to 001. This is the next byte. 0010, this is the another byte. All these are stored inside this block, and this is the block address. Okay, block mapping, as I said, block mapping is based on set index. For example, this particular block will map to this set number 7 because of this set index. I'm explaining all this thing in very quickly, because these are the basic concept of cache memory, and I'm assuming that you already know all this concept. For example, suppose here, suppose core is requesting for a block, and a core is requesting for an address like this, requesting for a word like this, or you can say core is requesting for read A, suppose, and this is the address of A. So in this case, based on this 3 red bits, it will go to set number 7, and A is stored here, suppose. Okay, now again process core is requesting for this address B, and now based on this site index, B has to map store in set 0. How it is storing? First of all, since there is a miss here, it will go to main memory and fetch the data from main memory and store it in this location. And then it will, from here, the requested data will be sent from here to core. Okay. Now next it is requesting for C. Now according to this index, it will go to 6. Now again it is requesting for D. Now according to this set index, it has to go to set number 6 again here. But in 6 there is a data called C already there, right? If the data called C is already there, then how to place a new data D here? Then you have to replace the old content. So the old data, that is CO, and this C will be replaced and the new data D will be placed here. Okay, this is also called a conflict because both C and D are mapping to the same set, and that is called a conflict also. So here C and D are conflicting with each other, though there are other empty places are already there in this case. For example, 1, 2, 3, these locations are free, but still C and D are conflicting based on this mapping policy of direct map cache. And this address 001 will map here, and then A for this A111, when core will request for this address here, see it will it is mapping here, but A is already there, so it will be a hit, so no need to go to main memory to fetch this data again. And in case of C also, if we go for C, then it is again mapping here, but now C has already replaced with D, so again there will be a miss here, and now we have to replace D with C because C and D are conflicting with each other. Okay, so we have to remember that this type of misses are called conflict misses. Why conflict misses? Because uh, even there is space available in this case, still this type of misses are occurring here, because now when you request for C, there will be a miss here because it is conflicting with D. So these type of misses are called conflict miss. And there is another type of miss, is called capacity miss. Capacity means that when the entire cache is full, and then you are requesting for a block and that is not possible to store here because the entire cache is full, then that is called capacity miss. And there is third kind of miss that is called compulsory miss. Compulsory means that any data when you are requesting at the beginning, then obviously it will be a miss, because as I said initially, that initially every data is in hard disk, right? From hard disk you will move it to RAM, and then from RAM, first of all, first time it has to come to cache. So the first time when you are fetching a data to the cache, it is called compulsory miss. Replacement policy I have already explained here. Replacement policy means if your data is conflicting with another data stored in the cache, then you have to replace the data and then to store a place the new data here. So replacement policy for direct map cache is very straightforward. You have to replace the data and store with the new data here. The structure of fully associative cache is completely opposite of direct map cache. So here there is only one set and multiple ways. If we compare this with direct map cache, you can see here there are only one way and multiple set. So fully associative set is just opposite of direct map cache. Since there is only one set, so set index is not required here. So tag address and set index are both called tag index here. So in case of fully associative cache, there is only block of set and tag address. It means that any block can be placed in any position of here. If there is any empty location, we can place a new block. For example, here assume there is a 16-bit address like this. If block size is 16 byte, then set index is not required. So and offset will be 4 bits, right? Because there are 16 bytes. So here there will be 4 bits will be required as a block offset, and remaining bits will be considered as tag address. Block mapping, as I said, block mapping, a block can be mapped in any place. So if we consider that these are the blocks that the core is requesting, then these blocks can be placed in any of these positions whenever there is a free location available. But once this cache is full, now if there is a new entry comes, for example, now if core requests for h, then there is no place left for h, then in that case we have to replace a block. So if we go for LRU replacement policy, means list recently used, then A is the oldest block here. So we'll replace A, in place of A, we'll place H here. This is the replacement policy. So one point that I have missed in previous slide also, that is searching. How exactly a searching is happening in direct map cache as well as in fully associative cache. So searching means here, for example, when a core will request for a particular block, then that block is first of all checked in cache memory, right? And if there is it is found in cache, it is called hit. So how we'll check, how we'll compare? So whenever we store a block here, with this block we also store the tag address. So whenever a new request comes, we know this tag address. So this particular tag address will be compared with the tag address corresponding to this block stored here. So if this tag address matches, then we'll say that this is a hit. So in case of direct map cache, there is only one entry per set. So there will be only one comparison for each set. If that comparison is fails, then cache it's a cache miss. But here, if in fully associative cache, if there will be multiple entries. So for all these entries, tag match has to be performed. So first of all, if you want to search a block, for example, the block is F, then you have to compare the tag match comparison should start from here. First it will compare here, then it will compare here, like this if it is a sequential comparison. And if it is a parallel comparison, then all the tag can be compared parallelly, means the tag of this, tag of this, and tag of all the blocks can become directly parallelly compared with this tag. But in that case, the hardware overhead will be much more, because there will be multiple comparators required, means one comparator for each block will be required. So a site associative cache is a intermediate between fully associative cache and direct map cache. So if we go for site associative cache, you can see it's a matrix-like structure, or you can say 2D array kind of structure. So here there are multiple rows. These rows are called set, and there are multiple columns also. So these columns are called ways. So if we compare with direct map cache, then direct map cache has only sets, multiple sets, and only one way. And if we go for fully associative case, there are multiple ways, but only one set. But in site associative case, there are multiple sets and multiple ways possible. So here the address is distributed like this. There will be block of set, and there will be set index to represent this set, and then there will be tag in the address both. So if we go for this, suppose this is called a four-way associative cache, because there are four ways or four columns are there. So now assume that this is again the address is 16-bit address, block size is 16 bytes. So number of site is 4 here. So the site index will be 2, right? So from here, index will be two site index is required. For example, if this is the address, then based on this, first 4 will be of offset, and then next to this 2 is considered as site index. So based on this value, we can say that this particular address is mapping to set number 3. That is, this is the set where it will map. And now in this set, this block can place in any of these four positions. If this position is empty, then this block can be placed here. But if all positions are full, for example, here all the positions are now full. So in that case, if we want to place a new block, then we have to call the replacement policy. So this is the block mapping policy. Each block mapped to a particular set based on the set index, right? And a block can be placed in any location or way, these are called way, within the set, within the map set. And then block searching policy is same. First of all, if we want to search a block, then first of all we'll select the particular set based on the set index, and in this particular set, all the tag will be compared with all the tags stored here. For example, if we fix this is the set, then here there are four entries available, so the tag of all these four entries will be compared parallelly. So in that case, there will be four comparator will be required here if we want to search it parallel. Okay. And replacement policy I've already explained. If any set the map set is full, then if you want to store a new block here, then you have to replace the old one. Okay, this is called replacement policy. So now if I quickly discuss about advantage and disadvantage of all these three techniques. So direct map cache advantage is easy to implement, easy to search, because you need to compare only one tag address, because there is only one entry per set. Disadvantage is collision. So there are many times there means a newly fetched block will collide with the existing block, because there is only one entry possible with this set. So collision will be more. Fully associative cache is the another extreme one. So here the advantage is less number of misses, the best utilization of cache possible. Why I'm saying best utilization? If you remember the example of direct map cache, at that time I have shown you an example between C and D, right? The C and D were conflicting with each other, but still at that time there are some empty space available in the cache, but still there was a conflict. That type of conflict will never happen in fully assertive case. You can say that in fully assertive case there is no conflict misses. Conflict misses is not possible. Only capacity misses and compulsory misses is possible in fully assertive case. In this way, it is very it is a very plus point. But the disadvantage is the hardware overhead. because if we want to search all the tag in parallel, then you need a lot of hardware over it to implement multiple comparators. Or if you go for a single comparator, then it will go for sequential search. It will be very, very time consuming. On top of that, also, even if you go for parallel sort, if there are multiple comparators, means one comparator for each block in full associative case, then also the time consumption will be more than set associative cache because of wire length. Because if I go back to this slide here, even if you have multiple one comparator for each block, but still, for example, for this comparator, there will be a long wire required to communicate with this comparator. So still, because of wire length, still the searching in sensitive case is expensive. So this is the disadvantage of, sorry, it's not sensitive cache, it's fully sensitive cache. It's expensive. And that's why by combining the advantage of both direct map cache and fully associative cache, set associative cache is proposed. So in set associative cache, advantage is less hardware overhead compared to fully associative cache, less number of collision compared to direct map cache, and less searching time compared to fully associative cache. Okay, so that's why most of the modern day cache are set associative cache. And in this course, I will assume only set associative cache. So whatever we'll discuss in terms of cache memory, everything will be in terms of set associative cache. We will not discuss about direct map and fully associative in this course. Which one is better? I'm not explaining it here. Set associative is better, but for some extreme cases, direct map as well as full associative cache can be better. You read the basic the computer organization book, you will understand it in more detailed way. Then the last point here is cache replacement policy. Replacement policy, I've already explained you that, uh, uh, but here the replacement policy I'm explaining is in terms of set associative cache. So as I said, in set associative cache, if you want to search a block or if you want to place a block, first of all, you have to set a set based on set index. So for example, suppose if you want to place a new block, then you have to first fixed a set based on set index, and suppose this is the set where you need to place. So in this case, if the new block is mapping here, you have to place it here. Even if there is a empty place here, you cannot place the block, you have to place it in this set because the set is fixed for a particular block in set associative cache. Okay, so now in this case, if the set is full, then you have to replace someone. Then which one to replace? So if, that point is very easy because you know that if you are following LRU replacement policy, then we'll replace the oldest one, right? In that case, if you say that A is the oldest one, then I will replace A with the new one, right? But LRU policy is not the only replacement policy. There are many replacement policy possible. But in all the replacement policy, there are three modules very important. First is insertion policy. Insertion policy means when a new data is coming, in which position you have to insert it. Promotion means whenever there is a access to a particular block or whenever there is a hit in that block, where to promote this block. And eviction means whenever the set is full, which block to be evicted. So if we concentrate on this LRU policy, that is list recently used policy, eviction policy is very easy. We all know for which block will be evicted. We'll remove the LRU block. This block that is in LRU position, that is list recently used position, will evict it. Insertion means whenever a fresh block will be placed here, we'll make it MRU. Means we'll make it as most recently used block. That is called insertion policy for LRU. And the promotion policy of LRU is whenever we'll access a block here, or whenever there will a hit to a block, we'll promote it to as MRU. We'll make it as MRU. This is most recently used block. So these are the eviction, insertion, and promotion policies for LRU replacement policy. These policies will vary for in different replacement policies. That will be discussed in next week. For example, suppose if this is the requesting sequence for A, B, C, and D in this set 0. So now okay, one more important point is this is actually cache set, right? Here the actual block is stored, actual block and its tag addresses are stored. So each set has a independent replacement policy. So this set maintains its own hardware unit for this replace to maintaining the replacement, and this set will maintain its own independent hardware unit. What I'm trying to say is the replacement policy is local for each set. This is called local replacement policy. So for this particular set 0, there will be a hardware unit to maintain the replacement policy. So suppose this is the hardware unit where here A, B, C, and D are written in this sequence A, B, C, D. So this is LRU, this is MRU. Now next request is E for this request is E. So next request is E here. We'll search E here. E is not here, so we'll fetch it from main memory. That is fine. But where to place? It is full, so we have to replace a block. So if LRU is maintained, then we have to evict. Eviction policy says remove the LRU block. So which one is LRU? Then you have to go to this LRU unit and check which one is LRU. A is LRU. So we'll remove A here. You will remove A here, and in place of A, we'll place E. Okay, so that is the placing the block is fine in cache. But what about the hardware means hardware unit of replacement policy here? So if we place E here, then this is called insertion. We are inserting. So what is the insertion policy? Insertion policy says then put it in MRU. So we have to remove A here, and E will be placed here. And this is the new architecture of new structure status of the replacement unit for set 0. Now if the next request is for a request is for D, so now when the next request is for D, then when we'll search it here, it will be hit here. Means D is already present in this cache. But in that case, the what should be the promotion policy? Means if there is a hit in or if we access a block in the cache, how to promote it? So LRU says promote it to MRU. So we have to make this D as MRU. So we'll not change anything here. This is the block. We will not do any swapping here. But in the replacement hardware, we have to swap these two. So it will look like this. So D is now MRU. So the point that I am trying to explain here is to maintain replacement, we no need to do any swap in this original cache. There will be a separate unit maintained for the replacement policy, and all this means removing this from, for example, from this state to this state. This is only change in this means additional unit which is used for replacement policy. So now in hardware, how exactly we implement it? So for example, here, how many positions are here in this set? There are four different positions here: one, two, three, four. So to uniquely represent the state of a position, how many bits is required here? 2 bits is required. So we can say that okay, 0 0 maybe 0 0 is LRU and 1 1 is MRU. So in this way, 2 bits is enough. 2 bits per location per way is enough to represent this LR means this LRU replacement policy for a particular set. So I hope the basic replacement policy is clear. The most important point, again, I'm repeating here, is replacement policy for set associative cache is local for each set. This is the first point. Second point is for each set there will be a replacement hardware unit where the replacement is maintained. And for here, for example, to maintain a replacement for this set, how many bits are required? 2 plus 2 plus 2 plus 2. So 8 bits are required. 8 bits are required for this to maintain LRU replacement policy. So all these basics, if you understand all these basics, then it is fine, because from next week we'll try to understand all means replacement policy in a more detailed or more advanced way, and what are the challenges of modern replacement policies, and all that we'll discuss from next week. So optimal replacement policies and all these are written here, but I'm skipping it for now because this is the advanced thing. So I'll explain all this point when I'll discuss replacement policy in more detailed way. So the last slide here is saying about different miss types: compulsory miss, capacity miss, and conflict miss. I think I have already explained it when I was explaining direct map cache. So I'm not explaining it here again. So at the end, I'm advising you again that whatever I've explained today are already written in this book, in this appendix. So basically, whatever I explained starting from that memory slide where I have written that from now onwards all the points are important, from that slide whatever I've explained, everything is written in this book or in this appendix C of this book. So please read it at least once, because I am again reminding you that your first quiz will be based on all these basics, all the basics based on memory. Maybe I'll not ask any question from pipeline, I'll not ask any question regarding instruction set architecture, but your complete quiz one will be based on the concept of cache memory, and that is available in this appendix. Okay, so thank you for watching this lecture one. If you have any queries, then you can ask me directly. You can ask your question through email, or you can also ask your question through Google Classroom. And next class will explain the basics of main memory. Thank you for watching this lecture.